Question 101, write an equation for each situation below showing that the area as a product is equal to the area as a sum. So if I look at this, there are four distinct regions, and I just need to basically multiply the column header by the row header to figure out the area of each of those regions. So for example, when I multiply 12x times x, I get that this is 12x squared. And then the box to the right of that, when I multiply x times 1, I get 1x. Below the 12x squared, when I multiply 12x times negative 5, I get a product of negative 60x. And then finally, negative 5 times positive 1 rather is negative 5. Negative 5 times positive 1 is negative 5. So if I go in now, it says that I'm supposed to show that the area as a product is equal to the area as a sum. What I would write for A is I would say that, hey, 12x plus 1, that's the dimension along the top, times x minus 5, that's the dimension off to the left, is equal to 12x squared. And then I'm going to combine negative 60x and 1 positive x, and that becomes negative 59x, and then finally minus 5. So in the one hand, I'm expressing the product as, the dimension, right? The length times the width. And the other one, I'm expressing the product as the sum of the parts of the area. But it's definitely noteworthy that these two areas are equal to each other. Let's try this for B. For B, we have, there's 6 regions here. We're going to combine them. In the upper left, I've got 3m times 2m squared. Well, 2 times 3 is 6, and I've got an m and then 2 more factors of m, so that would be m raised to the third power. That's m times m times m. To the right of that, I'd have 3m times negative 4m, which would be negative 12m squared. And to the right of that, I have 3m times negative 1, which is negative 3m. And then below, all the way over to the left, I have a 5 times 2m squared, which would be 10m squared. To the left of that, I have 5 times negative 4m, which is negative 20m. And then finally, I have 5 times negative 1, which is negative 5. So first of all, let's write it as the product of the dimensions. This would be 2m squared minus 4m minus 1. That's the dimension along the top. And that equals 3m plus 5. I'm sorry, times 3m plus 5. And then what it equals, if you take a look, I do have some like terms here, and it's kind of probably worth it to notice these ahead of time. One of the things I have is I have a 10m squared and a negative 12m squared. Those can be combined. And I also have a negative 3m and a negative 20m. Those can be combined as well. So if I rewrite the sum of the parts, just looking at it, I have 6m cubed. And then, like I said, I'm going to combine 10m squared and negative 12m squared. And that will combine as negative 2m. Negative 2m squared, rather. And then I'm going to combine negative 20m and negative 3m. That would be negative 23m. And then finally, I'm going to combine, or just write down the negative 5, the fact that there's a negative 5 left over. So that's B, and you can see again, I've got the product, the length times the width is the same as the sum of the parts. Now, C and D, they don't provide me with an area model, so I'm probably going to do this for quite a while. I'm going to sketch an area model and set up an appropriate one. And for C, the dimensions that I have, I can write a 2x and a plus 5, and then I could write an x and a 6 if I want. So if I look at them, I could figure out the area in each box. I have a 2x squared. The next box over is 5x, that's 5 times x. All the way the bottom row to the left, 6 times 2x is 12x. And then finally 6 times 5 is 30. So I'll write this in two ways. First of all, I'll write it as the product of the dimensions. So and actually it's the original problem, right? 2x plus 5 times x plus 6. And then what that equals is 2x squared. And you can see I've got 12x and 5x, which is plus 17x. And then finally, I've got 5 and 6, which is a plus 30. So if I'm multiplying 2x plus 5 by x plus 6, I get a product of 2x squared plus 17x plus 30. And then the final one I'll do in this beautiful Shasta High purple. You can see, I'm going to go ahead and set up a generic area model. That's what I call these. And I'm going to put a 3 and then a negative 5y along the top. And then I'm going to place a 2 and a positive y on the left-hand side. So figuring out the area of each piece, I've got 2 times 3 is 6. 2 times negative 5y is negative 10y. 3 times y is 3y. And then finally, I've got y times negative 5y, which would be negative 5y squared. Squared. So we can, just enough room to write D down below here. So the original problem was 3 times 5y, and the other part was times 2 plus y. And when I multiply those, after combining my like terms, I have a 6, and then I've got a 3y and a negative 10y, which would be negative 7y, and then finally I have a minus 5y squared. So that is my the sum of the areas, right? And the or the area as a sum, and then I've got the area as a product as well. Kind of more of the same. It says calculate each of the following products by drawing and labeling an area model, or by using the distributive property. Or by using the distributive property. That's an important thing to look at and be thinking about as you're looking at these. To be honest, the first one I probably would just do using the distributive property. However, I might write this out a couple times to make sure I understand exactly what's going on. So I have a monomial, right, negative 4y, and I'm multiplying that by a binomial, 5x and then plus 8y. So when I do that, I need to set up a 1 by 2 grid. So I've got my negative 4y here, and then across the top I've got a 5x and an 8y. Now, using the distributive property, right, I'm going to multiply this negative 4y times 5x, and I can see the same thing over here in my area model. When I multiply negative 4y times 5x, I get negative 20xy. And then next I'm going to multiply that negative 4y times an 8y. And when I do that, I'll get negative 32, right? Negative 4 times positive 8 is negative 32. And y times y is y squared. So that product is negative 20xy minus 32y squared. That's the answer. Let's try let's try B rather without the area model. Let's just try it with the distributive property. So I have 9x, and I'm going to multiply that by negative 4 plus 10y. And honestly, you really probably need to decide when you don't need to draw the area models anymore, and you can just accurately and consistently use the distributive property. So you make that decision. But to do the distributive property, I'm going to multiply both negative 4 and I'm going to multiply 10y by 9x. So when I do that, negative 4 times 9x is going to be negative 36x. And then 9x times 10y would be a plus 90, and I'll just write x times y. The last one, I don't think I'm going to finish with you. I'm going to, and I don't do that very often, but I think I want you to finish this. I will say that we definitely need to set up the generic area model, right? And I have something with 3 terms, so I'll put the 3 terms along the top, and I've got 2 terms going this way. So if I write down exactly what I have here, I've got an x squared, and then I have a -2, and then across the top there's an x squared, and then I'm multiplying that by a 3x, and then by a 5. So I want a separator between these problems. That's bothering me. There we go. So as I look at it, there's 6 different products I have to find, and then I can combine like terms and write it down. And just for instance, we'll look at just 2 of them. One of them we'll look at is what we get when we multiply the 3x and the -2. We would write -6 times x. That's part of our answer. And also, if I multiply x squared times x squared, if you just look at that, right, there's 2 factors of x, x times x, and then 2 more factors of x, x times x. So that's clearly x raised to the 4th power. So there's 1, 2, 3, 4 more that you need to do. Look for like terms and make sure you combine those when you write down what this area equals after using the distributed property, or in this case, a generic area model.
On graph paper, graph triangle ABC. If A is at -4, 3, B is at -6, 1, and C is at -5, 8. So I'm actually going to use the Desmos e-tool. I haven't done these before, certainly not on video. So this is what I get when I jump to that tool, and you can see I've got the points are already plotted there, and I have exactly all the points where they're supposed to be. This is point A. Point A is exactly at what is it? -4, 3. This is B. It's at -6, positive 1, and finally C is at -8, 5. And the first thing I'm asked to do is to rotate this triangle 90 degrees about the origin. So I think there's a preloaded sliding tool here. Yeah, here it is. So if I do that, this is what happens. And you know what, before I do it, I want to make a prediction. Take a look at this point. I think this is point A. This is the one they're asking me to track. This point has coordinates at -4, positive 3. Here at 4 and 3. If there's a 4, there's a 3. A -4 and a positive 3. Well, I know when I rotate 90 degrees clockwise or counterclockwise, I believe those points are going to switch places with each other. They're going to switch places, so it's going to end up being a 3 and then 4. But I don't know if the sign's positive or negative, but I think the -4, 3 is going to become 3, 4. And in fact, when I rotate it and it lands right there, notice this is exactly now at the point x equals 1, 2, 3, and y equals 1, 2, 3, 4. So it goes to positive 4, 3. This point that I had, which was at -4, positive 3, is now at positive 3, positive 4. So that's my answer to the first part, right? It says rotate triangle ABC 90 degrees clockwise about the origin to form triangle A prime, B prime, C prime. What are the coordinates of point A? Well, point A was here, right, and point A ends up here. So the coordinates of point A are at 3, 4. So we'll just put that up in our notes here. A is at 3, 4. And then it says apply the function that f of x is going to basically take all the x values and increase them by 5. It's going to take the y values and increase by 1. This time they're asking me to translate triangle ABCD. So I need to take the triangle that I just left off with. And I've done this incorrectly before. I've done this when they haven't called for it, but here they're saying, hey, you've done one transformation. We've rotated 90 degrees about the origin. This is where we started. This was a prime. This is now a double prime. Now the question is where does this point go after we apply this rule? Let's look at the rule again. It says basically you've got an xy point. We're going to take and we're going to increase the x value by 5, and we're going to, oops, I didn't want to close the parentheses, and we need to increase the y value by 1. So this is the translation we're going to do, and then they're asking where does point C go if we do this. So let's take a look. X values are going to get increased by 5. So here is the point A, and I'm going to go over 1, 2, 3, 4, and 5, and then the y is getting increased by 1. So I think this is my new A double prime, right? Before this was just A prime. Now I've got A double prime, and this was just A. I'm sorry. So I started with A, I got A prime, and now this is A double prime. Let's do that again for this point. So I'm going to go over 1, 2, 3, 4, 5, and then up 1 point. And I want to point out too that the internal consistency is really good. This was up 2 over 3. You got that same thing going on right here. To the right 2 and then up 3. And then one final point from here, we're going to go up over 1, 2, 3, 4, 5, and then up 1. So this is my new triangle after I apply this translation to it. And the translation rule basically just says take your x values, whatever it is, increase by 5, and take your y's and increase by 1. They were asking what are the coordinates of point C, and I forget where C was initially. C was at negative 8, 5, so negative 8, and then up 5. So this was point C, and then this went over here. This became C prime, and now this is C double prime. So my answer for C double prime ends up at 10, 5, 6, 7, 8, 9. 10, 9. So the location of C double prime is at 10, 9. On graph paper, graph the rectangle with the following vertices. Let's go ahead and do that real quickly. So the first vertex is at positive 2, positive 1. The next vertex is at positive 2, positive 5. Next we are at 7, 1, and then finally we are at 7, 5. Could have predicted that point. So let's go ahead and sketch this. Got it? And got it. And this problem says, what's the area of this rectangle? Well, I want to make a couple observations because I'm anticipating part B. Let's jot down these coordinates again. So this was at 2, 1. This was at 2, 5. The coordinates here are 7, 1, and the coordinates here are 7, 5. Well, take a look at this. Up and down is the change in y values, and if you look at this, I've got a y value that starts at 1 and ends at 5. And if I take 5 and subtract 1, I get exactly 4. So the height of this rectangle is 4 units. Now, obviously I could count that right now. It's pretty straightforward. I could see that it's 4. But I hope the reason why I'm pointing this out becomes clear in our next problem. The other thing I want to point out is if I take a look at this dimension, okay, this is the change in my x values, and for here x is starting at positive 2 and then x ends up at 7. Well, when I go from 2 to 7, I'm traveling 5 units, and I could get that by taking this value here, 7, and subtracting 2, and I get that it just increased by 5. So this dimension is 5. Again, I can count that. Now, 5 times 4 is 20. So the area for part A is, I'll write it right here, A is 20 units squared. But now let's jump to B. Shirley is giving the following points and asked to calculate the area, but her graph paper and mine either, they're not big enough, right? This is strictly too large. So calculate the area of Shirley's rectangles and explain to her how she can determine the area without actually graphing all these points. Well, what I'm going to do is I'm going to kind of try and do a crude sketch of roughly where these points are at. So for example, I've got a 352 and then up 150. So I've got this point 352 and then up 150. I'm just going to jot those down. 352, 150. Now this is a very crude sketch. The next point I have is 352, 175. And then I'm going to plot this point. It's going all the way over to x equals 456, and y is 150 still. It's silly that I ran out of room for that. And then the last point, x is still 456, and this time y equals 175. So I'm going to do the same thing I did before. This is the rectangle. I'm trying to find the dimensions of it so that I can calculate the area. Well, again, if I look at this, the change in these y values, right? Y is going from 150 to 175. And you can actually see that in both points, right? Here, y is 150, y is traveling up to 75. Well, I'm not great with arithmetic, but even I can figure out that if I take 175 and I subtract 150, I'm getting a change of 25 units. So this dimension, right, is 25 units because I'm, again, traveling from 150 to 175. 175 minus 150 is 25. The other dimension, if you take a look at it, x is 152, and it's traveling all the way up to 456. That's this dimension. So if I was to do that, just the arithmetic, I'll take 456, and I'll subtract 352, and yes, I'm going to put it in this column. 6 minus 2 is 4, and I have 104. So the change in x traveling from 352 to 456, x increases by 104. Well, that gives me exactly the dimensions of this rectangle. And if I do the multiplication, right, it's 25 times 104, and that's going to be the area. And actually, 25 times 100 is 2,500, and 4 times 25 is another 100. So I don't have a calculator here, but I'm pretty sure that the area of this is 2,600 units squared. And if it's not, I want to hear about it. Make sure you correct me tomorrow in class. So while Dave was solving the equation 100x plus 300 plus 500, he was wondering if he could first change this equation to x plus 3 equals 5. Dave's an insightful guy, right? Thinking outside the box. I like this Dave character. He says, what do you think? So solve both equations and verify that they have same solutions, if they indeed do. So on the one hand, right, we've got 100x plus 300, and that equals 500. And I can take away 300 from both sides. That gives me that 100x is equal to 200. And if I divide both sides by 100, I get x is 2. Over here, I've got the x plus 3 equals 5. And if I subtract 3 from both sides, I get x is 2. Interesting. So, yeah, they both have a solution of 2, and I can plug them back in. Yeah, 2 plus 3 is 5, and 2 times 100 is 200, plus 300 is 500, so they both check. Nice. It says, what could you do to the equation 100x plus 300 equals 500 to change it to the other one? Well, there's a lot of things I could do to that equation, but probably right now here, if you were to ask me, I would say either divide both sides by 100, or I would multiply both sides by 1 over 100. I need to be real clear. When I say divide both sides by 100, I mean that literally every single term on both sides would need to be divided by 100. And by terms, remember, we've discussed this vocabulary in classes with those things that are separated by addition or subtraction, addition of opposites. So on the left-hand side, 100x plus 300, if I divide each one of these by 100, right, each term by 100, I get x plus 3. And on the other side, if I do divide by 500, I get exactly, 500 by 100, I do get exactly the number 5. And you know, I'm kind of dissatisfied because I feel like I glossed over something, and I want to try and be a little bit more helpful. So when I'm looking at this, right, this is telling me that I've got 100x plus 300, and I need to divide the entire quantity by the number 100. Well, we're comfortable with looking at giant ones, and what I might do perhaps is I might say, look, at that numerator has a common factor of 100. Both of the terms in the numerator, 100x and 300x, can be divided by 100. So I can rewrite this as 100 times the quantity of x plus 3. And that's a totally numerator that's equivalent to the one up above. Now, if I show that I'm dividing this by 100, you can see real clearly I do have a giant 1, right? And when I eliminate that, I am left with exactly x plus 3. So bottom line, I do get x plus 3 is equal to 5, and therefore x is equal to 2. So that's a nice technique. Think about that technique, multiplying both sides by the same number in order to make your number smaller. Obviously, this is something that you've probably had practice with at some point or another, but for some reason, maybe you've never really quite gotten comfortable with dealing with arithmetic with rational numbers. So I'm going to do all parts of this. Don't watch this if you know how to do these. Move on. I want to point out one important thing. The goal here is for you to do this without a calculator. This is really critical because I want you to be able to think about these things in terms of algebraic expressions. And if we practice doing the arithmetic without our calculators with numbers, we're going to be able to do similar things with variables. So for this first problem, you can see I need a common denominator. The negative 2/3, right? I've got just a factor of 3 only, that's 1 times 3, and then I've got plus a negative 1/8, and that's just 2 times 2 times 2. So in order for these fractions to have the same denominator, I need to add some additional factors to each one. And precisely what I need to do is this fraction needs a factor of 3 in its denominator. So in order to keep it equal to negative 1/8, I'm going to multiply it by the number 1 in the form of 3 over 3. The other fraction needs a factor of 8 in its denominator, so I'm going to multiply it by 8 over 8. Now, the moment I do that, my numerator in the first instance becomes a negative 16, and then 3 times 8 is 24. On the other side, the other part, right, I've got a negative 3 and then a positive, or over 24. So I have the same denominator right now, right? They're both 24ths. I've got negative 16 24ths, and I've got negative 3 24ths. When I combine those, that's going to be exactly negative 19 24ths, and that's a great answer. Next one, positive 3 1/2 minus a negative 1 and then 1 3/2. One of the things that's tricky about mixed numbers is the fact that this 3 1/2 literally means a 3 plus a 1/2. And then I've got minus this negative 1 1/3 means a negative 1 and a negative 1/3, which is it's just what the notation means, and it's probably one of the reasons why I'm not a fan of mixed numbers. I prefer improper fractions. But looking at this, right, and rewriting it like this, you could think about our algebra tiles, and this part of it here would be like down in the negative region of our expression mats. So I can distribute a negative 1 to each one of these, right? Or I can think about this in terms of our algebra tiles and just bring these up to the positive part of the expression mat and flip their signs. So if I do that, either way, I get a 3 plus a 1/2, and then I get a plus a 1, and then I get plus 1/3. Now, if I look, I've got a 3 and a 1, super easy to bring those together, so that's just a 4. And then I still have a 1/2, and then I have a plus 1/3. And I'm going to build common denominators by introducing factors into each denominator so that they match. This particular fraction needs a factor of 3. I can see there's a factor of 3 next door and 1/3, so I need to build that into this fraction. And this fraction, 1/3, needs a factor of 2 in its denominator. At this point, they both have a 3 and a 2, and they're going to be common denominators then. So I've got a 4 plus, let's see, 1 times 3 is 3 over 6, plus 1 times 2 is 2 over 6. And 3 6 plus 2 6 is 5 6. My answer is 4 5 6. That's so much fun. Let's look at C. A multiplication problem. Ooh, I do know right off the bat, you know what, a negative number multiplied by a negative number, I'm going to be okay with that being positive. So to simplify my work, I'm not even going to think about those signs. The other thing I'm probably going to do is I'm going to go into a mixed number, and I'm sure almost all of you know the shortcut. 4 times 5 plus 1 is 4 1/5, right? The reason why that's the case, if you think about it, if I've got a 4 and I've got a 1/5, if I want to make these fractions with the same denominator, I multiply the 4 by a 5/5. So that's ugly how I've written it, but look what I have. I have 4 times 5 plus 1, which is 21/5. You can see where that comes from, I hope, right? Let's do the other part, and you can see. So part 1 I'm multiplying is 21/5, and let's look at the other part's just 1/3. So I'm going to multiply that times a 1/3. And you know what? If I look at that, I normally don't necessarily factor things out like this, but 21 is 3 times 7. So I'm going to write this as 3 times 7 times 1 over 5 times 3. The reason why I like that is you can see I have a giant 1. It's not lined up perfectly with each other, but I definitely have a 3 over 3. So that giant 1 is going to leave me a 7 in my numerator and a 5 in my denominator. I like that answer. I'm very fond of that answer. However, if you wish, you can, note that 5 goes into 7 exactly once, and I have a remainder of 2/5. So 1 2/5 is also a fine answer for C. On D, I have a negative, and I'm dividing it by a positive. So I'm going to get a negative number. Because of that, I'll just tell myself, hey, the answer is negative, right? And I'm not going to worry about the signs. But I've got 2/3. And I'm going to I'm dividing by 1/4, and I don't know if this seems like magic to you or what it is, but think about this. If I have 10 and I divide it by 1/2, I divide it into halves, right? 10 divided into halves. Well, how many halves are in 10, right? Well, 10 divided by a half is the number 20, right? And I can think about that in terms of a concrete objects. I've got 10 donuts. How many half donuts do I have? Well, I would have 20 1/2 donuts, right? There are 20 of them. So in general, what I like to do is think about this. If I'm dividing by a fraction, I just turn it into a multiplication problem. So 10 divided by 1/2 is the same thing as 10 times 2. So I end up getting the answer of 20. Okay, using that technology in our problem, right, I've got 2/3 divided by 1/4. I'm going to change that into 2/3 times 4 over 1. And when I make that switch, my numerator ends up being 8, and my denominator is 3. So my answer is 8/3. Hello! You told yourself to remember it was negative. I can see the negative symbol right there. So the answer is negative 8/3. That's my answer. And if you wish, 3 goes into 8 twice. 6, 7. It goes in twice with 2 left over. So I believe the answer could also be expressed as negative 2/3. And again, that trick, right? 3 times negative 2 is 6, plus, and then 2 more negatives is negative 8. Negative 8/3. All right, D. I'm sorry, that was D. Back to E. Looks like we're back to addition here. Yikes. So again, I'm going to bust this out. I've got a 1 plus a 3/4 plus, and then in parentheses I've got a negative 5, and I've got a minus 1/3. Yes, that is minus 1/3. Negative 5 1/3 is a negative 5 and a negative 1/3. So this is all in the positive region, so I'm not going to switch the signs when I bring things out of here. This is literally plus a negative 5 and plus a negative 1/3. So if I do rewrite this, though, I do get 1 minus 5. I think I can do that. Plus 3/4. And then I have a minus 1/3. Well, this, right, is going to be the number negative 4. And let's leave that for a minute. That's part of my answer. But again, I'm going to build the same denominators, right? So to do that, I'm going to introduce a factor of 4 in my thirds. So my common denominator is 12. And same thing over here, I'm going to introduce a common factor of 3. That's interesting. So when I simplify these, right, in the first case, that's kind of cool. I've got 3 times 3, 3 times 3 over 3. That looks like it's going to be 9 twelfths. And in the other part, I've got 1 times 4, which is 4, and then over 3 times 4, which is 4 twelfths. So I've got 9 twelfths minus 4 twelfths. 9 of them minus 4 of them is going to be positive 5. So I've got a positive 5 twelfths. Now, this is an unhappy day for me because I got to deal with the fact that I've got a negative 4, and I have to add to that 5 twelfths. Certainly, well, just a moment. So certainly one of the things I can do is I can rewrite the number 4 in twelfths, and I think that would probably be an intuitive way to handle this situation. So I could multiply this by 12 over 12, and that would give me, let's see, 4 times 12 is 24, 48. So this is negative 48 twelfths plus 5 twelfths. And if I combine negative 48 with 5, it gives me exactly negative 43 twelfths. And I have to say that was a tough problem, and I'm very happy with that answer. So we're just going to leave it there. If you want, you can convert it into a mixed number, but I'm very happy with that improper fraction. And then for the final problem here, I've got, it is division, and I'm kind of squinting to make sure, but it looks like it's negative 2 2/3 divided by negative 1 1/6. And we've talked about, this shortcut, why it is that I can, do these things. I'm going to definitely convert these into improper fractions. It's a lot easier to deal with in that situation. And I just want to, again, this is negative 2 and a negative 2/3. If I want these to have the same denominators, I would multiply this by 3 over 3. So this gives me a negative 2 times 3 minus another 2 all over the number 3. So the upshot of that is that's negative 8/3. And you can see this right here, right? 3 times 2 is 6 plus 2 is 8. So I have exactly negative 8/3. And I'm going to divide that by 6 times 1 is 6 plus 1 is 7, which is negative 1/7. No, I'm sorry, that's negative 7/6. And again, to divide, I'm going to invert and multiply. So this is negative 8/3, and I'm going to multiply by 6/7. I have a common factor here, or a giant 1, right? This can be thought of as negative 8. This is equal to negative 8 times 2 times 3 over 3 times 7. And we can see the giant 1, we've got a 3 over a 3. It's not all lined up nicely, but my final answer is negative 16 over 7.